In this video we will derive an expression for the mutual inductance of two coaxial solenoids. First you can take down this question so that you will be aware of what kind of question you may get in the exam. Deduce an expression for the mutual inductance of two long coaxial solenoids having equal length but having different radii and different number of turns. Deduce an expression for the mutual inductance of two long coaxial solenoids having equal length but having different radii and different number of turns. The first question is, what is coaxial? Coaxial, I think you know the meaning. Coaxial means common axis. So both the solenoids are placed in such a way that they have the common axis or their axis is same. So we'll draw a figure to represent these two coaxial solenoids. Now important points to note here is they are coaxial solenoids and having equal length, different radii and different number of turns. So no other quantities are given here. We can all assume, like for example, the first solenoid has n1 number of turns and has a radius of r1, etc. So we'll assume each and every quantity and then we will try to derive the mutual inductance. So first let us say we have two solenoids with common axis. So let me draw that. One is of radii r1, the other one is one is of radius r1 and the other one is of radius r2. Let me say this is my first solenoid and let me say the radius is, the radii of this is the radius is r1 for this. Okay. Consider another solenoid with the same axis. So here I will draw just one line so that it represents the axis, and now we will draw another solenoid. Let us say the radius of that solenoid is r2 and I'll assume r2 is greater than r1. It can be reverse also, no problem. And I will take this red color to represent that solenoid. I'll just draw it once again. Sorry. This is one solenoid and I'll draw another one like this of greater radius. and one is radius r2, the other one is r1. Let us say the first one is, so this is number 1 solenoid, and this, let us say this is number 2. Two solenoids numbered as 1 and 2. Let the length of the solenoid as n, that is they have equal length. Let we are passing a current I1 through any one of the solenoid. I'll say I'm passing a current I1 through the first solenoid. Now we will write all these quantities, whatever we have done till now or whatever we have assumed. So let L is the length of solenoids. Length of solenoid 1 and 2, because they have equal lengths. R1 and R2 are the radii of solenoid 1 and 2 respectively. Okay, so let n1 is the number of turns. Solenoid has a number of turns. Let solenoid 1 has n1 number of turns. Let solenoid 2 has n2 number of turns. Okay, so now we have assumed all the quantities. Now when a current I1 is passed through solenoid 1, what happens? A magnetic field is set up. So we can write the magnetic field in solenoid 1 due to current I1 is magnetic field set up or magnetic field due to current I1, magnetic field due to current I1 in solenoid 1 as B1 as, what is the formula? B1 is mu naught into small n1 into I1. What is small n1? Where small n1 is capital N1 by L, that is number of turns per unit length. This is by basic formula, and this formula we have derived already in the previous chapter. So B1 is mu naught N1 I1, and where N1 is N1 by L is the number of turns per unit length. What is this? Number of turns per unit length. Now due to this current, a magnetic field is set up, and this magnetic field produces flux, and that flux also links the second solenoid. So we can find out what is the flux which is linking the second solenoid, because we want to find out the mutual inductance, that is flux in the second solenoid due to the flow of current in the first solenoid. So we can write total flux linked with solenoid, second solenoid. Solenoid 2 as phi 2, which is equal to B1 into A2 into number of turns in the second solenoid. Now we can substitute this B1 and N2 here. N2 is, if you want, you can write it as N2 into L, or let it be N2 itself, no problem. So B1 is mu naught into N1 I1 into, so A2 also you can write in terms of the radius, pi R2 square into N2. So now pi R2 square into N2. Next, what is mutual inductance? By definition, mutual inductance is given by mutual inductance M as phi 2 by I1. So why did we find out phi 2? Because mutual inductance is phi 2 by I1. Now phi 2 we have, substitute that, divided by I1 you can do. So M is mu naught into N1 I1 into pi R2 square into N2 divided by I1. So this I1 will get cancelled. So we have the equation, for M as M is equal to mu naught into pi R2 square into N1 N2, or we can substitute N1 as N1 by L. Substitute N1 is equal to N1 by L. What do we get? M is equal to mu naught into pi, this is just pi R2 square, not pi square, pi R2 square, into N1 by L into N2. So this is the value for M. M is mu naught pi R2 square into N1 N2 by L. Or you can write in terms of area also. So this is one equation for M. M is mu naught pi R2 square into N1 N2 by L. Or you can also write it as M as mu naught into A2 into N1 N2 by L. One in terms of area and another one in terms of radius. M is mu naught A2 into N1 N2 by L. This is the required expression. So the required expression in this case you can write in terms of R2 because the radii is given. They have different radii like that. Or you can also write in terms of area. So here we have substituted pi R2 square as A2. The mutual inductance or coefficient of mutual induction for two coaxial solenoid is given by mu naught into A2 into N1 N2 by L, where L is the length of the solenoid, N is the number of turns in the first solenoid, N2 is the number of turns in the second solenoid, and A2 is the area of the second solenoid. And I hope you understood this derivation.